Welcome to another episode of My Weird Prompts, an AI-generated podcast featuring the random prompts of Daniel Rosehill as answered by a revolving cast of friendly AI characters. Join us for deep dives into AI, technology, and whatever other random thing Daniel finds fascinating today. Subscribe on Spotify or your favorite podcatcher. Now, today's episode.
This episode was generated using artificial intelligence. Please verify facts.
Hi there, Herman and Corn. So a great technology that we touched upon recently and related to storage is that of RAID. Very much associated with NAS, network attached storage, but also used, of course, widely in the world of servers. And RAID does something really amazing, which is allows your computer to, or allows a storage system to survive the failure of a hard drive. And certain forms of RAID are able to do more than that. You can actually have some types of RAID that can allow you to survive multiple disk failures, which when you kind of, I guess, look at it statistically, the chance of one hard drive or SSD failing at any point in time and without warning are probably already fairly small. And then if you think the chance of multiple ones all failing at exactly the same time, then you're really getting down to a very, very, such a small degree of probability that it's kind of de minimis. But it is incredibly useful. It does come with a trade-off in that you have to trade some of your space for RAID, and the more redundancy you get, the more space you have to trade. So it's a bargain, but it's a very good bargain, and it's a very important form of redundancy that allows probably a lot of data to be preserved that would otherwise be lost. And in multi-volume computers, logical volumes, it's very helpful too. RAID is not backup. Maxim you'll see repeated a lot in the backup world, but it's certainly very useful. So I'd love to know a little bit more. I know that there's many types of RAID that are out there that are possible. I think I'm running RAID 5 on my computer. I have 5 disks, and I got up to that seemingly absurd number of internal hard drives based upon the best type of RAID. I wanted to get 1 disk redundancy, and I think that was like how many I had to stack together before I could do that. But I'd love to know about the different types of RAID that are out there and how does this actually work if I do have that, if I do have disk failure. And I've seen this actually happen on an NAS in which you can expand the pool. So you kind of, it almost makes me think of a starfish that it can regrow. It's almost like you cut off a leg and it miraculously keeps that data and then allows you to actually grow the pool. And that's where I think it's really, really impressive. Not all types of RAID can do that, and there's other types of mechanisms for data parity and data spreading that we can talk about. But just at the very basic, I'd love to get a handle on the different types of RAID, how this technology actually works. I know it's very mathematical, spreading out bits basically across different storage systems. Who came up with this? It's a brilliant piece of technology. And besides the ones I've mentioned, NASs, where do we see this tech actually deployed in the real world?
Hey everyone, welcome back to My Weird Prompts. I am Corn, and I am joined as always by my brother,
Herman Poppleberry, ready to dive into the bits and bytes. It is January 8th, 2026, and we have a classic technical topic today that is near and dear to our household.
It really is. Our housemate Daniel was just telling us about his latest computer build. He is finally moving away from those old 10 terabyte drives and has stepped up to a 5-disk RAID 5 array using next generation, roughly 30 terabyte heat, assisted magnetic recording, or HAMR, drives that are now starting to hit the market. He sent us a prompt asking about the history, the math, and the different flavors of this technology.
I love that he is running RAID 5 with 30 terabyte drives. It is such a classic choice, but in 2026, it carries some really terrifying trade-offs that most people do not think about until a drive actually clicks its last click. We are talking about roughly 120 terabytes of nominal usable capacity before formatting and file system overhead, which is incredible for a home lab. But the rebuild math on drives that size is a nightmare.
Exactly. And I think it is important to set the stage here. We have talked about storage before, like back in episode 151 when we discussed network setups, but RAID is specifically about how we handle the inevitable failure of physical hardware. Herman, for the uninitiated, what are we actually talking about when we say RAID?
Well, the acronym stands for Redundant Array of Independent Disks. Interestingly, when it was first conceived in the late 80s, the I stood for inexpensive. The idea was that instead of buying one massive, incredibly expensive mainframe-grade hard drive, which they used to call a sled or single large expensive disk, you could string together a bunch of cheap consumer-grade disks and make them act like one big, fast, reliable unit.
That is a great bit of historical context. It was a shift from relying on the perfection of a single component to building a system that could handle imperfection. Who actually gets the credit for that shift?
It mostly traces back to a 1987 paper from the University of California, Berkeley. David Patterson, Garth Gibson, and Randy Katz published A Case for Redundant Arrays of Inexpensive Disks. They presented it at the SIGMOD conference in June of 1988. They basically laid out the blueprint for everything we use today. They realized that as disk drives got smaller and cheaper thanks to the PC revolution, the real bottleneck was not just capacity, but performance and reliability. If you have one big sled and it fails, you are done. If you have 5 disks working together, you have options.
I love the term SLED. It sounds so heavy and industrial. So the Berkeley team basically said, let's use the power of the many rather than the power of the one. But they didn't just invent one way to do it, right? They came up with a whole list of levels.
They did. They originally defined RAID levels 1 through 5. Over the years, we have added RAID 0, RAID 6, and various nested levels like RAID 10 or RAID 60. But before we get to the popular ones, we should probably mention the ones that time forgot. RAID levels 2, 3, and 4 are basically history lessons now.
Why is that? What happened to them?
RAID 2 was super complex. It striped data at the bit level and used something called Hamming codes for error correction. It required a massive number of disks just for the parity information. RAID 3 striped at the byte level, and RAID 4 striped at the block level, but used a single, dedicated parity disk. The problem with RAID 4 was that every single time you wrote data to any disk, you had to update that one parity disk. It became a massive bottleneck. RAID 5 solved that by spreading the parity across all the disks, which is why RAID 4 is mostly a ghost in the machine today.
Okay, so let's walk through the ones people actually use. The different RAID levels can be a bit of a soup of numbers. Most people hear RAID 0, RAID 1, RAID 5, and their eyes glaze over. Let's start with the simplest one, even if it is a bit of a misnomer when it comes to the redundant part of the name.
Right? RAID 0? I always say the 0 stands for how much data you have left if one drive fails. RAID 0 is all about striping. Imagine you have a long sentence to write down. Instead of writing the whole thing on one piece of paper, you write the first word on paper A, the second word on paper B, the third word on paper A, and so on.
So you are basically splitting the data across 2 or more disks. The benefit there is speed, right? Because you can read from both disks simultaneously.
Exactly. You are doubling your throughput. In 2026, with PCIe Gen 6 NVMe drives, a RAID 0 array can reach speeds that are frankly ridiculous. We are talking about tens of gigabytes per second. But, as you pointed out, there is zero redundancy. If disk A dies, you have half of every sentence missing. The entire array is toast. It is not a matter of if you lose data, but when.
It is a high wire act. Great for temporary scratch space or video editing where you have the original footage elsewhere, but terrifying for a primary storage volume. So, what is the polar opposite? That would be RAID 1, right?
Exactly. RAID 1 is mirroring. This is the simplest form of actual redundancy. You take 2 disks and you write the exact same data to both of them at the same time. If disk 1 dies, disk 2 is a perfect clone. You just keep on working.
It is the ultimate peace of mind, but the cost is high. If you buy 2 30-terabyte drives, you only get 30 terabytes of usable space. You are paying a 50% tax on your storage capacity.
It is a steep price, which is why we do not see RAID 1 used for massive datasets. It is great for your operating system drive where you just need it to work no matter what. But if you are Daniel and you have a massive library of media or research data, you want something more efficient. That brings us to the king of the home server world, which is RAID 5.
This is what Daniel is running with his 5 disks. And this is where the math gets really cool. RAID 5 uses something called parity to provide redundancy without losing half your space. Herman, how do you explain parity without a whiteboard?
It is actually quite elegant. Think of the exclusive or operation, or XOR. In the world of binary math, XOR is a simple rule. If you have 2 bits and they are the same, the result is 0. If they are different, the result is 1. So, 0 XOR 0 is 0. 1 XOR 1 is also 0. But 1 XOR 0 is 1.
Okay, I follow that. But how does that help me recover a lost file?
Imagine you have 3 disks. Disk A has a bit of data, let's say a 1. Disk B has a 0. To create the parity bit for disk C, you XOR them together. 1 XOR 0 equals 1. So disk C stores a 1. Now imagine disk A fails. We look at what we have left. We have a 0 on disk B and a 1 on disk C. If we XOR those together, 0 XOR 1 equals 1. We just recovered the missing bit from disk A. It is beautifully symmetrical. You can have 4, 5, or even 10 disks, and as long as you XOR all the data bits together to get the parity bit, you can always solve for the missing variable if one disk fails.
That is incredible. It is like an algebraic equation where you can always solve for x as long as you only lose one variable at a time. So in a RAID 5 setup, you are basically spreading those parity bits across all the drives in the array.
Precisely. We call it distributed parity. In Daniel's 5-disk setup, the system treats the capacity of 4 disks as usable space, and the equivalent of 1 disk's worth of space is used for parity. But it is not just one dedicated parity disk like in RAID 4. The parity information is rotated across all 5 disks. This prevents a single disk from becoming a bottleneck during writes, though there is still a performance hit because every write requires a read. Modify write cycle to update that parity bit.
So he gets 80% of his total raw capacity, and he can survive any single drive failing. That feels like a great deal. But I have heard you mention before that RAID 5 has a bit of a dark side, especially as hard drives have gotten massive. It is 2026, and we are seeing 30 and 40 terabyte drives now. Why is RAID 5 risky there?
It comes down to the rebuild time and the math of unrecoverable read errors, or UREs. When a drive fails in RAID 5, the array is in a degraded state. To get back to safety, you have to put in a new drive, and the system has to read every single bit on the remaining 4 drives to calculate the missing data for the new 5th drive.
And with a 30 terabyte drive, that is a lot of reading.
It is a staggering amount of reading. Even at a sustained speed of about 200 megabytes per second, it would take on the order of 40 hours, getting close to 2 full days of non-stop reading to rebuild a 30 terabyte drive. In reality, with system overhead and other tasks, it can take many days. On heavily used systems, it can stretch toward a week or more. During that entire time, your remaining disks are working at very high utilization, generating heat and stress. If a second drive fails during that rebuild process, the entire array is lost.
And the probability isn't 0, right?
Far from it. Many consumer and NAS class drives have an unrecoverable read error rate specified around 1 in 10 to the 14th to 10 to the 15th bits. That sounds like a lot, but 10 to the 14th bits is only about 12.5 terabytes. If you are rebuilding a 100 terabyte array, the statistical likelihood of hitting a read error on one of the surviving drives is actually quite high. If you hit that error during a rebuild, the controller often just gives up and marks the whole array as failed. This is why many enterprise admins say RAID 5 is effectively dead once you get into multi-terabyte drives, especially above 2 to 4.
This is why I've seen more people moving toward RAID 6, right?
Exactly. RAID 6 is like RAID 5, but with double parity. It uses 2 different mathematical equations, usually XOR and a more complex Reed-Solomon code to store redundant data. This means it can survive the simultaneous failure of 2 drives. You lose the capacity of 2 disks, but you gain a massive amount of safety during that long rebuild process. If Daniel had 6 disks instead of 5, I would have strongly suggested he go with RAID 6. In 2026, many storage engineers consider RAID 6 the practical minimum for large spinning disks built from very high-capacity drives.
It is interesting how the technology has to evolve just to keep up with the physical scale of the hardware. Speaking of evolution, there is another level that people often confuse with RAID 0 or 1, and that is RAID 10. Or is it RAID 1 plus 0?
It is RAID 1.0 or a stripe of mirrors. This is the gold standard for performance and reliability if you can afford the disks. You take 4 disks and you pair them up. Disk 1 and 2 are a mirror. Disk 3 and 4 are a mirror. Then you stripe data across those 2 mirrors.
So you get the speed of RAID 0 because you were striping, but you get the redundancy of RAID 1.
Correct. And the rebuild is much faster than RAID 5 or 6 because you aren't doing complex math. You are just copying data from the surviving twin of the mirror. It is very popular in high-performance databases where every millisecond of latency matters. The downside, of course, is that you lose 50% of your capacity. If Daniel used RAID 10, he would only have 60 terabytes of nominal space instead of 120.
I want to circle back to something Daniel mentioned in his prompt. He talked about how the system can grow, like a starfish regrowing a limb. But he also touched on something that I think a lot of people get wrong. He said RAID is not a backup. Herman, why do we need to shout this from the rooftops?
Because it is the most dangerous misconception in all of computing. RAID protects you against hardware failure. It does not protect you against human failure, software failure, or environmental failure. If you accidentally delete a file, RAID will dutifully delete it from all your mirrored or parity disks simultaneously. If a piece of ransomware encrypts your data, RAID will help it encrypt that data across your entire array with maximum efficiency.
Or if your power supply surges and fries every disk in the chassis at once.
Exactly. RAID is about uptime. It is about making sure your server stays online even if a mechanical part breaks. Backup is about recovery. You need a separate copy of your data on a different device, preferably in a different physical location. We usually talk about the classic 3-to-1 rule, and these days, some data protection folks extend that into a 3-to-1-1-0 rule. 3 copies of your data on 2 different media, 1 off-site, 1 offline or immutable, and 0 errors after verification. If your data only exists on one RAID array, you do not have a backup. You have a very sophisticated single point of failure.
That is a sobering thought. But let's look at the brighter side. Where else is this technology being used? Daniel mentioned NAS units, which are common for home labs and small businesses. But RAID is everywhere, right?
Oh, absolutely. If you use any cloud service, whether it is for photos, email, or document storage, your data is living on some form of RAID or its modern successor erasure coding. In massive data centers like the ones run by Amazon or Google, they aren't just using 5 disk arrays, they are using massive distributed systems that act like RAID on a global scale. They might break a file into 10 pieces and add 6 parity pieces, then spread those 16 pieces across 16 different servers in 3 different buildings. That way, an entire building could burn down and your data would still be safe.
I imagine the financial sector is a huge user as well.
Huge. Think about high-frequency trading or even just your local bank's transaction ledger. They cannot afford for a single hard drive failure to halt trading or lose a record of a deposit. They use hardware RAID controllers with dedicated processors and battery-backed cache memory. This ensures that even if the power goes out in the middle of a write operation, the data stays in the controller's memory until it can be safely committed to the disks.
That brings up a technical nuance I wanted to ask you about. I have heard the term write whole in relation to RAID 5. What is that, and why should Daniel care?
The write whole is a classic RAID 5 problem. Imagine the system is writing data and calculating the new parity bit. If the power cuts out after the data is written, but before the parity bit is updated, you now have a mismatch. The next time the system tries to use that parity bit to recover data, it will calculate the wrong result. Modern systems use things like journaling file systems or non-volatile RAM in the controllers to bridge that hole, but it is a reminder that these mathematical systems are still bound by the laws of physics and electricity. This is why a good uninterruptible power supply, or UPS, is mandatory for any RAID setup.
It is amazing how much engineering goes into just making sure a 1 stays a 1 and a 0 stays a 0. Now, Looking at the year 2026, we are seeing a shift away from traditional hardware RAID towards software-defined storage. Things like ZFS or BTRFS. How do those differ from the classic RAID Daniel is using?
That is where it gets really exciting. Traditional RAID is often invisible to the operating system. The OS just sees one big disk. But software-defined storage, like ZFS, is aware of both the disks and the file system. It uses something called checksums. Every time it reads a block of data, it verifies it against a known mathematical signature.
So it can detect bit rot.
Exactly. Standard RAID can tell you if a drive has failed completely. But what if a drive is still spinning, but it just happens to flip one single bit because of a cosmic ray or a minor magnetic flaw? A traditional RAID controller might not notice. It will just hand that corrupted data to the user. ZFS sees the checksum mismatch, realizes the data is wrong, and uses the parity information to automatically repair the corrupted bit on the fly. We call it self-healing storage. It also eliminates the write hole problem entirely by using a copy-on-write architecture. It never overwrites data. It always writes new data to a new block and then updates the pointers.
Self-healing. That really does sound like the starfish analogy Daniel used. It is a much more intelligent way of handling data integrity. So, if Daniel ever decides to rebuild his system, maybe a move to a ZFS-based setup like TrueNAS would be a good next step for him.
I would highly recommend it. Though, knowing him, he will probably want to jump straight to a 10-disk RAID Z3 array just to see if he can make the lights in the house flicker. RAID Z3 is the ZFS version of triple parity, meaning he could lose 3 drives and still stay online.
He does love his hardware. You know, thinking about the broader implications of this, RAID really changed the economics of the entire internet. By making it possible to use cheap, mass-produced disks for mission-critical tasks, it lowered the barrier to entry for everything from web hosting to streaming services.
You are spot on. Without RAID, the cost of storing a petabyte of data would have remained astronomical for much longer. It democratized high-availability storage. It is one of those invisible technologies that hums along in the basement of the digital world, and we only notice it when the little red light on a server tray starts blinking. In 2026, we are seeing this evolve into AI-driven storage management, where the system can predict a drive failure before it happens by analyzing vibration patterns and latency spikes.
I love those kinds of technologies, the ones that are so successful they become invisible. Herman, we have covered a lot of ground here, from the Berkeley paper in '87 to XOR math and the dangers of the RAID 5 rebuild. What are the big takeaways for someone like Daniel or any of our listeners who are managing their own data?
First, understand your RAID level. Know the difference between striping for speed and parity for safety. Second, be honest about your drive sizes. If you are using massive 30 terabyte drives, RAID 5 is simply not enough protection anymore. You need RAID 6 or RAID 10. Third, and I will say it again, RAID is not a backup. Have an off-site immutable copy. And finally, look into software-defined storage. The intelligence that ZFS or similar systems bring to data integrity is well worth the learning curve.
Solid advice.
Yes, please do. We love hearing from you. And if you want to see the show notes or find our RSS feed, head over to myweirdprompts.com. We have all our past episodes there, including the ones we mentioned today.
This has been a great one. Thanks to Daniel for the prompt. It is always fun to dig into the mechanical and mathematical heart of our machines.
Absolutely. It makes me want to go check the health of our own arrays right now.
Probably a good idea. Thanks for listening to My Weird Prompts. I am Corn.
And I am Herman Poppleberry. We will catch you in the next one.
See ya.
We should really talk about erasure coding next time. It is like RAID, but for the cloud era.
Oh, I am sure Daniel will have a prompt about that soon enough. He is already looking at distributed file systems for his next project.
Of course he is. The man never sleeps.
Neither does his server. All right, let's go get some coffee.
Oh, sounds like a plan.
One last thing for the listeners. If you have a weird prompt of your own, something that keeps you up at night, or something you have been tinkering with in your home lab, send it our way through the contact form at myweirdprompts.com. We might just dedicate an entire episode to it.
We love the technical ones, but we are open to anything. The weirder, the better.
Exactly. Until next time, everyone, stay curious.
And keep your backups current?
Especially that. Bye!
This episode was generated using Gemini Flash 3. Text-to-speech engine was Chatterbox Turbo.
Thanks for listening to another episode of My Weird Prompts, an AI-generated podcast featuring Daniel Rosehill's AI prompts, as answered by a revolving cast of friendly AI characters including me, Cornelius the Sloth. Subscribe on Spotify or visit myweirdprompts.com.